Welcome to The Explainer. Today, we're going to peel back the layers of artificial intelligence to reveal how machines actually, think. I am absolutely thrilled to guide you through this material because we're literally looking under the hood of systems that are rapidly changing our entire world. Let's just dive right in.
Here's our blueprint for building an artificial brain. We'll cover 1. Meeting the intelligent agent, 2. The engine, which is optimization, 3. Storing knowledge and logic, 4. Formulating a master plan, and 5. Learning from the real world.
Section 1. Meet the intelligent agent. What is AI?
Let's start with a really fundamental question. We throw the term AI around all the time in daily conversation, right? But before we can actually build an AI, we really have to define exactly what it is we're trying to create. I mean, how do we measure if a piece of silicon and code is actually intelligent?
Well, in the study of AI, we look at intelligence through the lens of an agent. You can think of it kind of like a highly advanced feedback controller. Basically, it's an input-output system. It takes in observations from the world using sensors, cameras, data feeds, things like that, and then it executes actions to actually change that environment. Its behavior is ultimately driven by a mathematical function. That function determines its absolute best next move, based entirely on everything it's observed in the past.
Now, crucially, not all agents are trying to do the exact same thing. We generally split them up into two camps. First, we have believable agents. These are the ones designed to act like us. They model human emotion and behavior. Think of the lifelike characters in your favorite video game, or maybe a conversational voice assistant. But then we have rational agents. And these agents, they really don't care about acting human at all. They are completely driven by the goal of maximizing their performance on one specific task. That could be winning a world-class game of chess or just navigating a robot vacuum around your living room couch. For this explainer, we're going to focus squarely on these rational agents.
Section 2. The engine. Optimization.
So, now that we've met the rational agent, let's peek at the underlying engine that drives all of its decisions. How does it actually choose what to do? Well, the secret sauce here is optimization. Optimization is really just this pure mathematical desire to find the absolute best answer. Imagine our agent is blindfolded in a super hilly landscape, and it's trying to find the lowest possible valley, because that lowest point represents the lowest error or the absolute best performance. It uses local search techniques to sort of feel its way around. It might use gradient descent, which is literally just taking steps down the steepest slope it can find. Or it might use hill climbing, where it evaluates every single neighboring option. And to avoid just walking in circles forever, it uses taboo search, keeping a running memory of where it's already been. It's like remembering not to touch the same hot stove twice, right? There's also simulated annealing. This is a super clever technique where the agent makes wild exploratory jumps early on, but gradually settles down to exploit the best area it found. It's actually a lot like slowly cooling metal to remove structural defects.
And this brings us to one of the most fascinating optimization techniques out there, digital evolution. We call this a genetic algorithm. Instead of just one agent looking for a solution, imagine an entire population of them, all represented as strings of code. The algorithm takes the fittest solutions, the ones performing the best, and essentially breeds them. It creates a crossover, literally splicing the best parts of two parent solutions together to make an offspring. Then it introduces random mutations, just to ensure the new generation doesn't get stuck in a rut. It is literally survival of the fittest, just mathematically engineered.
Section 3. Storing knowledge and logic. Okay, having established the optimization engine, let's move on to the agent's memory. How does it store what it knows about the world? And more importantly, how does it draw logical conclusions from all that knowledge? Well, just like we need language to organize our complex thoughts, an AI agent uses structured logic. It might start out with propositional logic, which deals in strict true or false statements. But as we know, the real world is incredibly complex, right? So agents often upgrade to first-order logic. This allows them to actually grasp objects, their properties, and how they relate to each other. It gives the agent the power to deduce things. For example, if it knows Fido is a poodle and it knows all poodles are dogs, it can firmly conclude that Fido is a dog. And the crazy part? It does this even if you never explicitly programmed that final fact into its code.
But what happens when the real world gets messy? Because let's face it, reality is rarely perfectly true or perfectly false. Let's say an agent is sorting machines by weight. Exactly when does a medium machine officially become a heavy machine?
To handle these wonderfully vague concepts, agents use what's called fuzzy logic. Instead of a rigid yes or no, the agent assigns a membership degree, a number between 0 and 1. This allows the AI to understand that a 35-kilogram machine is, well, sort of medium, but also kind of heavy. It's a real game changer because it enables much more nuanced, realistic decision-making. Now, to speed up all this complex reasoning, agents also use these visual mental filing cabinets called semantic networks. Instead of slowly searching through massive text databases, concepts are represented as individual nodes, which are then connected by relationship edges. The agent can rapidly trace the lines between these concepts to infer inherited properties. So, just by following the relationships, it instantly knows that because Fido is a poodle and poodles are dogs, Fido definitely has the ability to bark. It's basically a highly efficient shortcut for machine thought.
Section 4. Formulating a master plan.
All right, so our agent has its optimization engine. It's got memory and it understands logic. But how does it actually figure out the necessary steps to reach a real physical goal? Simply put, it needs a plan. Planning for an AI is essentially bridging the gap between a start state and a goal state. Think of it exactly like trying to solve a sliding 8 puzzle. The agent looks at the jumbled starting numbers, and it knows exactly what the organized goal state should look like. Planning is just the optimization task of finding the absolute shortest, most efficient sequence of moves to get from point A to point B.
The really crucial point here is exactly how it maps out that journey. An agent obviously can't physically test every single possibility, not when millions or even billions of combinations exist. Instead, it builds a massive mental search tree. And to navigate that tree efficiently, it uses informed search techniques, like the A-star algorithm. You can think of A-star as a kind of heuristic compass. It constantly estimates the cheapest path to victory. By evaluating which specific move gets it fundamentally closer to the goal, the agent can safely ignore thousands of useless moves and totally zero in on the winning strategy.
Section 5. Learning from the real world.
And finally, we reach the last major lobe of the artificial brain, machine learning. This is how an agent actually acquires knowledge without you having to explicitly program every single rule for it. It's amazing because machine learning beautifully mimics human experience. An agent can learn via supervised learning, where we essentially act as the teacher. We feed it thousands of labeled examples, like showing it exactly what a spam email looks like, over and over until it spots the pattern. Then there's unsupervised learning, where it finds hidden structures in raw, chaotic data completely on its own. Or it can use reinforcement learning. This one is literally exactly like learning to ride a bike. The agent experiments in its environment, falls off, gets some negative feedback, adjusts its approach, and tries again and again until it's riding smoothly.
But here's the catch. The agent's ultimate learning challenge is something called the bias variance dilemma. I like to call it the Goldilocks problem. In one scenario, you have underfitting. This is where the agent's model is way too rigid, way too simple, and it just completely misses the underlying trend. But on the flip side, you have overfitting. This happens when the agent adapts so wildly to every single tiny bump and bit of noise in the training data that its model becomes totally chaotic. It essentially memorizes the training data, but becomes completely useless for predicting anything new.
So how does it find that just right balance? Well, agents employ incredibly clever mathematical tricks called regularization techniques. A really popular one is lasso regression. You can think of lasso as a strict mathematical penalty for being too complicated. It literally forces the agent's learning model to stay as simple as possible while still accurately fitting the data. This actively prevents that chaotic overfitting we were just talking about. It ensures the AI actually learns the underlying lesson so it can successfully generalize its knowledge out in the messy, completely unpredictable real world. And honestly, that brings us full circle. You now understand the true anatomy of an AI agent. We've seen its optimization engine furiously searching for the best path. We've explored how it uses logic to reason, how it builds a master plan to hit its goals, and how it learns from pure experience without needing to be explicitly programmed. These are not just abstract concepts, folks. They're the exact mechanisms driving the intelligent automation that's integrating into literally every sector of our society right now. So the question I want to leave you with today is this. Now that we're successfully mapping these core cognitive functions on machines, what incredible, complex problems are we going to ask these digital minds to solve for us next? Thank you so much for joining me for this explainer. And as always, keep your curiosity sharp.